Hey everyone, it's Dr. Doctor, and so today I'm going to be giving you some notes about vectors. Woohoo! So hopefully you've had a chance to read through chapter 1, especially towards the end of chapter 1, where they talk more in detail about vector addition. So we're going to be using vectors more when we get into two-dimensional motion for later in the week, and then next week when we get started on forces, the vectors will become even more important. We'll see them again later on in momentum too. All right, so I'm going to share my iPad screen so I can give you some of these notes. All right, here we go. So if you've learned about vectors before, you know that they have both a magnitude and a direction, and we usually represent vectors like an arrow. And so we represent the magnitude or the size of the vector with the size of the arrow. So if you've got, like an arrow like that, the size or the length of that arrow would be the magnitude. The direction would be indicated by the direction of the arrow. If you have a smaller magnitude vector, you wouldn't draw it quite as long. All right, so if you need to add up vectors, like if you wanted to add these two vectors, you would just put them in a row and you would get an overall vector that is the total length of both of them. But if you have vectors that are at an angle, you have to consider what are called the components of those vectors. So if you're going to look at vector addition, when things are at an angle, then you're going to have to draw it out and figure out the components. So the way that you figure out components is you draw a coordinate system. So let's say we have an x direction and we have a y direction. And we have some kind of vector here, which is just going to be like, I'm just going to label it a vector v. So if we wanted to know what are the components of this vector, it's at some angle theta, we would look kind of at the projection of that along the x-axis and along the y-axis. So if we drew something like a dotted line here, we would look at this as being the y component of that vector. And along this side, we have what we would call the x component of that vector. And so if you've learned trigonometry, maybe you heard this abbreviation SO, ka, TOA. So what that stands for is the sine of an angle is the opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So if we're going to look at the sine of this angle, and I'm going to call this like this length of the side to be the magnitude. So that's one way that we can represent the magnitude of that vector with sort of absolute value signs around it. So the sine of theta is going to be the opposite side, which is Vy over the hypotenuse. And so the magnitude of that vector, we'll just call it V. So if we want to know what the y component of vector V is, we would say that that y component, then we multiply both sides by V and we get V sine theta. If we're going to look at the cosine of the angle, then we're going to see that it's Vx over V. And so Vx, the x component of that vector, is V times the cosine of the angle. And sometimes it'll be useful to use the tangent, but typically we'll use it to figure out what the angle is. So we would do the opposite over adjacent, which is Vy over Vx. I'm using also sort of V because we'll be seeing that in velocity later this week. All right, so if you want to know the magnitude of the vector, you can also think about the Pythagorean theorem. So the a squared plus b squared equals c squared, or the vx squared plus vy squared equals the magnitude of the vector squared. So if you want to know just the magnitude of that vector v, you're going to have that vx squared plus vy squared and take the square root of it. All right? So that's how you would find the magnitude of that vector. Now we're going to talk about another way to write the component form using what's called unit vector notation. And so you can draw a coordinate system in 3 dimensions. So if you like to have x to the right and y up, then your z direction would, you have to picture this coming out towards you. And if we're going to designate unit vectors, we're going to call them I hat, j hat, and k hat. And so they have this little caret symbol on top of them. So I is a unit vector, which means that it's a vector of magnitude 1 that points along the x direction. So we would call this like your I hat. Your j hat is going to point here along the y direction, and your k hat is going to point here along the z direction. So if you want to represent something like our vector v in this unit vector notation, we would say that the vector v is the x component along the I hat direction plus the y component along the j hat direction. And so you could also write this as v cosine theta in the I hat direction plus v sine theta in the j hat direction. All right, so this is the component form using unit vector notation. So you can also do this coordinate system with z upwards. Sometimes people like to have z upwards, but then you need to make sure that you have y to the right and x coming out at you. This will be important if you're going to take 204. We'll see this again later, but you don't want to put x to the right and y coming out. That's not going to be what's called the right-handed coordinate system. That would be a left-handed coordinate system, so you can use either one of these. All right, so let's try an example of adding vectors. All right, so we've got maybe some generic vector A and generic vector B. And if we add them, we're going to get some kind of resultant vector R. So we're just going to call that the resultant when we add them. So let's say A is going to be 5 I hat plus 6 j hat. Sometimes we'll have units in here, so just have to keep track of things. B vector is going to be 6 in the I hat and a -2 in the j hat direction. So if we want to just add these in terms of this components, we can add up the I hat components and add up the j hat components. And we would say that our resultant there in unit vector notation is 11 in the I hat plus 4, because 6 minus 2 is 4, in the j hat direction. If you want to know the magnitude of that resultant vector, remember to get the magnitude, we're going to have to do the x component squared plus the y component squared and take the square root. And so we would have 11 squared plus 4 squared and take the square root of that. And if you put that into a calculator, you would get about 11.7 as the magnitude of that resultant vector. So if you want to kind of verify that, and actually we could figure out what the angle is too. So we'll sketch it out and we'll also find this angle. So You can use the tangent of theta is going to be equal to ry over rx. So theta is equal to the inverse tangent of ry over rx. So theta is the inverse tangent of 4 over 11, which would give you around 20 degrees for this problem. So if we're looking at this, we could see that the, if you want to know what that angle is with respect to, so what I usually do is I sketch it out. So if my resultant is 11 along the x-axis and 4 along the y-axis, you'd have to draw some little tick marks in here. 5, 6, 7, 8, 9, 10, 11. And I'm going to go up 1, 2, 3, 4. And so my resultant looks something like this. And so if you found your inverse tangent of your ry over your rx, that would mean that this is your angle here. And so I would say that that's 20 degrees above the positive x-axis. So 20 degrees above the positive x-axis. Sometimes you may have things in a different quadrant and you'll have to describe if it's above or below a particular axis. If you're actually looking at the original vectors that we started with, vector A and vector B, you can also do something called the graphical method or the tip to tail method. So if we're looking at like a graphical way of looking at this, we would have to look at what was vector A and what was vector B. All right, so vector A was 5 in the I hat and 6 in the j hat. So vector A was something like this. And then vector B was 6 in the I hat and negative 2 in the j hat. So we go one more this way and 2 down. And your B, something kind of like that. So if you're going to use the graphical method or the tip to tail method, what you do is you take your vector A and you're going to put your vector B with the tail of vector B at the tip of vector A. So I'm just going to see if I can kind of copy over the A, what it looks like. It's kind of something like this. And then if you're going to put B at starting at the tip of A, now you'd have to do something like that. And if you're looking at the resultant, you go from where you started to where you ended, and your resultant vector looks like this one. And you can see that kind of looks like the resultant vector that we had before in this picture over here. All right, so if you have something that's at maybe a different angle or a different quadrant, maybe you have like A going off to the left. And then you had a B going up into the right, something like this. So now if you say that A is your first vector and you're going to add B to it, you're going to shift your B over so that the tail of B is at the tip of A. And so you'd still have your A vector, but Now you're going to put B at the tip over here. And your resultant would actually go from here, where A started, back up to here. All right, so we'll do some example problems with these, and also for your next homework assignment, homework 2, you'll see you have some vector questions to solve as part of that problem set. And so you'll get to practice if you have multiple vectors, maybe not just 2, but maybe you have 3 or 4 vectors. You can add them using the graphical method where you put them tip to tail. You might also be given angles for a particular vector rather than knowing what it was in component or unit vector notation. So in that case, it might be useful to have access to a ruler and a protractor, even if it's an electronic version, so that you can map out what is the length of a particular vector and what is the direction, and then add them up tip to tail so that you can find out what the direction and the magnitude of the resultant vector is. All right, so that's going to wrap up these notes on vectors. And let us know if you have some questions about this, and watch the additional example problems that we're going to do too.